Imagine you have a messy pile of colored LEGO bricks, and you want to line them up from smallest to biggest. If you try to compare every brick with every other brick, you will spend a lot of time, like looking at each pair one after another. Divide and conquer is a clever way to cut the work in half again and again. First, you pick a special brick called the pivot. Then you split the whole pile into two smaller piles. Bricks smaller than the pivot go to the left, bricks larger than the pivot go to the right. Now each of those smaller piles can be sorted in exactly the same way. Because we keep breaking the problem into smaller pieces, the total amount of work becomes much less than comparing every pair. This idea is needed for sorting because it lets us handle huge lists quickly, just like sorting a big bookshelf by first dividing it into sections and sorting each section separately. The partition step is the heart of quick sort. Think of a row of toys on the floor. You choose one toy as the pivot and then walk from the left end and the right end toward the middle. The left walker moves right until it finds a toy that is bigger than the pivot. The right walker moves left until it finds a toy that is smaller than the pivot. When both walkers have stopped, you swap the two toys, then the walkers keep moving. When the walkers cross, the pivot is swapped into the exact spot where everything on its left is smaller, and everything on its right is larger. Doing it in place means we only use the original array, we never need an extra copy of the whole list. In code 2, indexes I and j walk toward each other, and we swap Ri and Rj whenever the conditions above are met. After the loop stops, we put the pivot at index I. This uses only a few extra variables, constant space, and rearranges the original array directly. Choosing the pivot is like deciding where to cut a cake, so the pieces are about the same size. If you always pick the first or last element, a sorted or reverse sorted list gives you a tiny left piece and a huge right piece. The cuts are very uneven and the algorithm slows down. Common strategies. First or last element, simplest but can be bad for already ordered data. Random element, pick a position at random. The chance of always getting a terrible cut is tiny. Median of 3, look at the first, middle, and last elements and use the middle value as pivot. This often gives a more balanced split. Median of a sample, take a small random sample, for example 5 elements, and use its median. The better the pivot approximates the true middle, the faster the sort, because the two subproblems become roughly half the size each time, leading to the ideal O of n log n behavior. Let T of n be the expected number of comparisons quicksort makes on an array of n items. When we pick a pivot uniformly at random, the pivot could end up in any position k, 0 less than or equal to k less than or equal to n-1. If the pivot lands at position k, we must sort a left part of size k and a right part of size n-1 minus k. The cost of partitioning itself is linear, theta of n. T of n equals 1 over n times sigma from k equals 0 to n minus 1 of t of k plus t of n minus 1 minus k plus theta of n. The term 1 over n is the probability that the pivot lands at each possible k. Because the sum is symmetric, the two t terms are the same on average, giving T of n equals 2 over n times sigma from k equals 0 to n minus 1 of t of k plus c times n for some constant c. Multiply both sides by n. N times t of n equals 2 times sigma from k equals 0 to n minus 1 of t of k plus c times n squared. Now write the same equation for n minus 1 and subtract. N times t of n minus 1 times t of n minus 1 equals 2 times t of n minus 1 plus c open parenthesis n squared minus open parenthesis n minus 1 close parenthesis squared close parenthesis. Simplify the right-hand side. Equals 2 times t of n minus 1 plus c open parenthesis 2n minus 1 close parenthesis. Rearrange to get a recurrence. T of n equals t of n minus 1 plus 2 over n times t of n minus 1 plus O of 1, which also equals t of n minus 1 times open parenthesis 1 plus 2 over n close parenthesis plus O of 1. Unfolding the product from 2 up to n yields a harmonic series, which grows like log n. Consequently, t of n equals theta of n log n. Thus the expected running time of quicksort is O of n log n, even though any single run might be faster or slower. Another common proof uses the fact that each pair of elements is compared at most once, leading to n times ceiling of log base 2 of n expected comparisons. The worst case happens when the pivot is always the smallest or the largest element. In that situation, the partition creates one subarray of size n-1 and another of size 0. The recurrence becomes T of n equals T of n minus 1 plus theta of n. Solving it gives T of n equals theta of n squared, the same cost as the naive bubble sort. How can we avoid this bad luck? Randomized pivot. Choose the pivot at random. The probability of repeatedly hitting the worst pivot is 1 over 2 to the n, practically 0. Median of 3. Using the middle of first, middle, last often prevents the pivot from being an extreme value on already sorted data. Intro sort, start with quick sort, but if the recursion depth exceeds 2 times log base 2 of n, switch to heap sort, which guarantees big O of n log n worst case. Hybrid with insertion sort. For tiny subarrays size less than or equal to 10, use insertion sort. This reduces the chance of deep, unbalanced recursion. These tricks keep quicksort fast in practice, while protecting against the pathological O of n squared scenario. Quicksort uses recursion, so each recursive call adds a stack frame. If the recursion depth is log base 2 of n, the balance case the extra space is big O of log n. When the pivot is unlucky, the depth can become n, leading to big O of n space. Tail recursion optimization helps by converting the second recursive call into a simple loop. After partitioning, we recursively sort the smaller side first, then continue on the larger side. Because the larger side size shrinks each iteration, the maximum stack depth stays bounded by log n even in the worst case. In languages that support tail call elimination, for example Scheme or some functional languages, the compiler can remove the extra stack frame automatically. In imperative languages like C, C++, or Java, we do it manually with a while loop. Thus, the space usage of quicksort is typically big O of log n auxiliary space, and with tail recursion it can be made almost constant big O of 1 for the larger portion of the work. Real-world programs add a few practical tricks. Hybrid with insertion sort is extremely fast for arrays of less than or equal to 10 to 20 items because it has low overhead and uses the already sorted part as a guide. Quicksort stops recursing when the subarray size falls below a threshold and runs insertion sort on the whole array at the end. Cache-friendly partitioning. Modern CPUs read memory in blocks called cache lines. By accessing elements sequentially during partition, we keep the data in cache, reducing slow memory accesses. Some implementations use a two-pointer method that scans the array once and swaps in place, which is cache optimal. Loop unrolling. Small loops inside the partition step can be unrolled to reduce branch mispredictions. Avoiding recursion altogether. An explicit stack, an array of index pairs, can replace recursive calls, giving better control over memory and allowing iterative implementations. Choosing a good cutoff. Empirically, a cutoff of 12 to 16 works well on most machines. This value can be tuned per hardware. Two popular modern flavors of quicksort are randomized quicksort dash. Before each partition, pick a random index as the pivot. This turns the worst-case O of n squared scenario into a probabilistic event with negligible chance. Many textbooks present this version because the analysis becomes cleaner. The expected O of n log n bound holds for any input. Dual pivot quicksort dash. Instead of one pivot, pick two pivots P and Q. P less than or equal to Q. Partition the array into three parts. Elements less than P, elements greater than or equal to P and less than or equal to Q. Elements greater than Q. Then recursively sort the three regions. Java's arrays.sort for primitive integer uses this algorithm because it reduces the number of swaps and comparisons on average. The expected complexity stays O of n log n, and the constant factor is often smaller than classic single pivot quicksort. Both variants keep the core divide and conquer idea, but improve robustness, randomized, or performance. Dual pivot. They illustrate how a simple algorithm can evolve over time to meet the needs of modern hardware and large-scale data.